Section 3.5, Transformation of Functions. Here's a table of a few basic functions and their graphs. We've already seen linear functions in the past. The most basic linear function is f of x equals x. In the previous homework, you should have seen and graphed the absolute value function, which makes this v shape. A few other very popular functions that we may be working with in the future are quadratic functions and cubic functions. Notice the graphs above. Quadratic functions are parabola shaped. Cubic functions kind of have this S shape to it, but sideways S. The square root function, which is the top half of a sideways parabola. The cube root function, which looks like a cube function, just turned sideways. And two other obscure ones are reciprocal functions and the 1 over x squared functions. All of these functions have very well understood graphs, and the question becomes, from understanding these basic functions, how can we obtain the graph of other functions? Or if we're given a graph similar to one of these graphs, what would be the equation of that function that would generate such a graph? The way we're going to obtain graphs from variations of our basic functions, or to obtain the equation of a graph that is a variation of a graph from our basic function, is through transformations. There are three types of transformations. There's shifts/translations, there's reflections, and then there's stretches and compressions. Shifts or translations are indicated by adding or subtracting a value. And there's two ways we can translate a graph. We can either translate it vertically or we can translate it horizontally. If we're adding or subtracting a value to our function, but outside of the function, this indicates a vertical translation or vertical shift. If we're adding the value, we're shifting up that many units. If we're subtracting a value, we're shifting down that many units. Horizontal translations are indicated by adding or subtracting a fixed value directly to x inside of the function. Be very careful with what the operation tells us about the translation. If we're adding c to x inside of the function, we shift left. But if we're subtracting c to x inside of our function, we shift right. The reflections are indicated by multiplying by a negative value. And there's two types of reflections. We either reflect over the x-axis or the y-axis. We reflect over the x-axis if we're multiplying by -1 outside of the function. If we're multiplying -1 to x inside of the function, this results in reflecting over the y-axis. And our last family of transformations are the stretches and shrinks, or stretches and compressions. Keep in mind that compression and shrink are synonyms, so we will use those interchangeably, just like translation and shifts are also synonyms and will be used interchangeably. If we're multiplying our function by some fixed value a, this is going to result in a vertical stretch or compression. What determines whether you're a stretch or a compression is the size of a. If the absolute value of a is greater than 1, our graph is being stretched. But if the absolute value of a is between 0 and 1, then we're being vertically shrunk or vertically compressed. One thing to note, a can be positive or negative. If a is positive, then we are not reflecting. But if it is negative, then we also have a reflection over the x-axis at the same time. Next, we also have the horizontal compression, which is indicated by multiplying a value directly to x inside of the function. Now, the compression or the shrink is also determined by the size of b, but be very careful the rules are opposite than that of the vertical stretch or shrink. If b is greater than 1, this is going to result in a horizontal compression. On the other hand, if b is between 0 and 1, this results in a horizontal stretch. One thing to note that's important on this table is how each transformation affects the points on the graph. Notice that if we're translating, we're adding or subtracting the value to the corresponding component. If I'm shifting up the units, I'm adding d to the y component. If I have to shift left, c units, I'm subtracting c from the x value. Similar with the reflections, if I'm reflecting over the x-axis, I'm changing the sign of all the y components. But if I reflect over the y-axis, I'm changing the signs of the first component. Luckily, stretches and compressions do have the same rules. If I'm doing a vertical stretch or compression, I am multiplying my y value by a. But if I'm doing a horizontal stretch or compression, I'm dividing all my first components by b. Make sure you pay special attention to these rules. Change in the coordinate points are a big part of how we obtain graphs from our basic functions. This slide shows what we visually expect from the various transformations. For example, when we're doing translations, whether vertical or horizontal, notice how the resulting graph in red just looks like the blue graph just moved around a little bit. For example, the one here on the left, you can see going from the original absolute value graph to this absolute value of x minus 1. It's as if we picked up the graph and moved it down 4 units. Same thing when looking at the square root of x versus the square root of x plus 5. It looks like we picked up the square root of x graph and moved it left 5 units. Looking at the pair in the middle, they showcase the reflections. Notice how each graph just looks like we spun it 180 degrees over the axis that we chose to reflect over. The bottom pair shows a visual display of the compression. Notice how in each of the compressions, whether vertical or horizontal, it looks like the graph was squished from the sides. In the case of the vertical shrink, it looks like we grabbed the graph from the top and the bottom and we pressed downwards, while the vertical stretch or shrink, we grabbed the graph from the left and the right and pressed inwards. For the vertical stretches or the horizontal stretches, just imagine instead of compressing, what would happen if you stretched out the graphs. Next, we're going to write the formula of a function g of x based off of how we would obtain g of x by performing our translations to f of x. So here, f of x equals 3x cubed. If g of x is the graph of f of x shifted up 3 units and left 6 units, we're going to write the formula for g of x. So to start, we know g of x is going to equal some transformation of our f of x. Now let's fill in what is happening to our function either outside of the function or inside of the function. First, we're told we're shifted up 3. Well, vertical translations affect outside of the function. Anything that causes a change vertically does happen outside of the function. And since we're shifting, that means we're adding or subtracting. So we're going to add or subtract 3 outside of the function. Well, since I'm shifting up, we're going to add 3 outside the function. Next, we're told we're going left to 6. Since we're going left, that's a horizontal transformation. Horizontal transformations are indicated inside the function. So we know directly to x, we're either adding or subtracting 6. Since we're still shifting, we're translating 6 units to the left. But be very careful. The way we can tell if we're shifting left is if we see x plus some number. So be very careful with the signs. When you're shifting left, we're adding a number directly to x. Now that I know that g of x is supposed to equal f of x plus 6 plus 3, I can now take the x plus 6, plug it in to f of x, which is 3x cubed, and I get g of x equals 3 times quantity x plus 6 cubed plus 3. If g of x is the graph of f of x vertically stretched by a factor of 2, then shifted down 5, right 2, we're going to write a formula for g of x. Using the same strategy as before, we know g of x is some transformation of f of x. Since we know we are vertically stretched by a factor of 2, because it's a vertical transformation, we know it will affect outside of the function. And if you go back to how vertical stretches or shrinks are performed, we'll be multiplying to outside of our function. Next, we're told we're shifted down 5. Well, shifting down is a vertical transformation, which means it affects outside of the function. Since we're shifting, we're adding or subtracting 5 outside of our function. And since we're shifting down, we'll subtract. And lastly, we're shifting right 2. Well, shifting right is a horizontal transformation, so we know directly to x because it's a shift, we're adding or subtracting 2. But be very careful once again, since we're moving right 2, we're going to subtract 2. To get the final formula for g of x, we're going to plug x minus 2 in for x and g of x, and we're going to multiply that result by 2 and subtract 5. And with a little cleanup, multiplying the 3 and 2, we get 6 times quantity x minus 2 cubed minus 5 as our formula for g of x. And for our last example, if g of x is the graph of f of x reflected about the x-axis and horizontally stretched by a factor of 3, we're going to write the formula for g of x. Using the same strategy, we know g of x is a transformation of f of x. Our first transformation is a reflection about the x-axis. Reflection about the x-axis is a vertical change, and it's indicated by multiplying our function by a negative value. We'll just multiply outside by -1 because our problem doesn't mention anything about a vertical stretch or shrink. Now, we do have to be very careful with our next transformation. Which is a horizontal stretch. With a horizontal stretch, we know we have to multiply inside of our function some value directly to x. The question is, what should be multiplied to x? If I just multiply by 3, which it does seem tempting to do, we would have a bit of a problem here. Because if you go back to the table, 3 would be b, but the absolute value of 3 is 3, which is greater than 1. So by writing 3x, I actually have a horizontal compression. We want a horizontal stretch. So instead of having 3, we're going to put the reciprocal, 1/3, and multiply that to x. Now, 1/3 is between 0 and 1, so we do have a stretch. Now that we've identified that g of x equals negative f of 1/3 x, we can plug 1/3 x into our function and remember that negative on the outside. So g of x equals negative 3 times the quantity 1/3 x cubed. The graph on the right is obtained by transforming the graph of y equals x squared. We're going to write an equation of the function that we have graphed here on the right. The hard part about trying to write the equation for this curve after we've done the transformation is trying to figure out what transformations were used. Let's start off by graphing the y equals x squared graph, and then slowly move it around using our translations, our stretches and shrinks and reflections to see how we can make the graph of y equals x squared into the graph that we see. Recall that the graph of y equals x squared is a parabola. The points in purple are the points I want to keep track of. These are the points 0, 0, 1, 1, and -1, 1. The reason why I'm picking these 3 specific points is they're numbers that are very easy to square. 0 squared is 0, 1 squared is 1, -1 squared is also 1. Now I'm going to slowly try to figure out what transformations we're using to make our parabola into the red graph. As we go along figuring out the transformations, we're going to start one at a time to see how that affects our equation y equals x squared. So at the very start, we're starting with f of x equals x squared. And I'm using f of x, the function notation instead of y, to make it a little bit easier to piece together how the transformations affect the function based off the table we were provided at the very beginning. Now, the first thing I notice when I compare the two parabolas are the opening. Our starting parabola for the y equals x squared, notice how it opens upwards, looking like a bowl that's holding water, while our red parabola is upside down, looking like a bowl that's dumping water. So the first thing I would want to do is I would try to flip this graph of y equals x squared upside down, so that way both parabolas are now opening in the same direction. So my first transformation I would try is I'm going to try to reflect my graph over the x-axis. Now, as for my points, when I reflect over the x-axis, that results in me multiplying all my y values of each point by -1. Well, the point 0, 0 is going to stay at 0, 0, since 0 times -1 is 0. As for the point 1, 1, well, 1 times -1 is -1, so my point 1, 1 would reflect down to the point 1, -1. And for -1, 1, for the same reason, -1, 1 would reflect down to -1, -1. Then I'm going to make my parabola. Now, because I'm reflecting over the x-axis, my parabola would open downwards. So there's my graph after reflecting my starting parabola over the x-axis. Now, the next part of where to go can be a little tricky depending on whether or not we need a stretch or a compression. Notice here how the top point of my blue graph down to the 2 points that I'm tracking. In order to go from the 2 points I'm tracking, I would either have to go left or right 1 and then up 1 unit. If I take a look at my highest point on my red graph, go down 1 unit and then left or right 1 unit, notice how it's 2 points on the parabola. So essentially my parabolas here have the same width, which tells me I don't have to stretch or shrink at all. So now that I know I don't have to worry about stretching or shrinking, the next thing I'm going to do is the translation. Well, how do I determine how to move my graph? Well, I'm going to use the top points to help me. Judging by how I would have to move the top point of my blue graph to my red graph, I would have to go up 2, right 1. Now, it doesn't matter which order you choose to go, whether you want to go up first and then right, or right and then up. Our third transformation is going to be up 2 units. And then our fourth transformation is going to be right 1 unit. And when we see that and then from there, we can see that if I do go from each of my points that I'm tracking, up 1, right 1. And I can see that if I trace up 1, right 1, I can see if I trace up 2, right 2 from each point I'm tracking on my parabola, I do end on another point of my parabola. So by shifting my entire blue graph up 2, right 1, I now overlap perfectly with my red graph that I wanted to find the equation for. But now that I know how to obtain my red graph from the starting graph f of x equals x squared, now we can go through and apply the rules for the transformation. After the reflection, if I call my resulting function g of x, from my table of how we tell when a certain transformation is used, g of x would have to equal negative f of x, and f of x is x squared, so that would be negative x squared. Now from g of x, we shifted up 2 units. So if I call my resulting graph when I shift up 2 units h of x, because I'm transforming g of x, that's going to equal g of x plus 2. Plus 2 outside because we went up 2 units. Well, g of x is the negative x squared, so my h of x is negative x squared plus 2. And then lastly, after we do 1 unit up to obtain our final graph, let's call this function now k of x. Well, because I'm moving right 1 unit, this would be h of x minus 1. In h of x, we're going to replace x with x minus 1, and we get k of x equals negative the quantity x minus 1 squared plus 2. What is the equation of the function for this graph? You can either use the function notation calling it k of x or g of x or f of x, or without function notation, we would replace the k with a y. But we get y or k of x equals negative the quantity x minus 1 squared plus 2. Now, we've discussed before one way we can classify functions is based off if they're one-to-one or not. We also like to classify functions based off of their symmetry. We call these functions even or odd functions. A function f of x is said to be even if f of negative x equals f of x. Even functions are symmetric with respect to the y-axis, since if we have the point xy on the graph of f, then negative xy is also a point on the graph of f of x. Another way to interpret the property of an even function, specifically f of negative x equals f of x, is that reflections over the y-axis don't change the graph. A second way to think about this property is it doesn't matter the sign of the number we plug in. Because f of negative x equals f of x, if I plug in a negative number, I'm going to get the same answer that I would get if I just dropped the sign to begin with. Classic examples of even functions are the x squared and the absolute value of x functions. If you go back and look at their basic graphs, you can see that they do have the symmetry with respect to the y-axis, where if we fold our coordinate plane along the y-axis, both halves of the graph will perfectly align. For our next classification, a function f of x is odd if f of negative x equals negative f of x. Odd functions are said to be symmetric with respect to the origin. Now, what does it mean to be symmetric with the origin? If we have the point xy on the graph of f, then the point negative x, negative y is also on the graph of f of x. The way we can tell that a graph is odd visually is we would imagine taking our graph, folding it along the x-axis, and then folding it along the y-axis. At that point, both halves of the graph should perfectly line up. Classic examples of odd functions are the x cubed function and the cube root of x function. In this example, we're going to determine if the following functions are even, odd, or neither. For our first graph on the left, we can tell that it's not even because if we fold our coordinate plane along the y-axis, which I've highlighted in green, we can tell that both halves will not line up. If we take a look at this point down here that we know is on the graph, which has the coordinates 0.6, negative 0.4, if we did have the symmetry with respect to the y-axis, meaning it was even, then we should also have a point on the other side of the y-axis where we switch the sign of the x component. Well, if we switch the sign of the x component while keeping the y component the same, we wind up at the point negative 0.6 and negative 0.4, which we can see is not on the graph. Next, we'll check to see if the graph is odd. In order for a graph to be odd, if we have the point xy, then we also have the point negative x, negative y, which means if we have a point on the graph, if I switch the signs of both components of the point, the resulting point should also be on the graph. Well, if I switch the signs of both coordinates, if I switch the signs of both components of my point, I get negative 0.6, 0.4, which we can see is on the graph. Now, to be on the safe side, we'll also check another pair to make sure the property still holds. If we take a look at this point here, it has the coordinates 1.4, 1.4. Well, if I switch the sign of both components, I wind up down here at the location negative 1.4, negative 1.4, which is also on the graph. So our function defined by this graph must be odd. For our second graph, if I fold my graph on the y-axis, which I have highlighted in green, we can definitely tell visually that both halves would line up perfectly. So just by a visual inspection, we can tell that this graph is even. If we take a look at the third graph, well, we can definitely tell it is not even. If I fold along the y-axis, we can definitely tell both halves will not line up. Let's check to see if it's odd. If I take a look at this point here, which is the point 1, 2, In order for this function to be odd, then -1, -2 would also have to be a point on the graph. But -1, -2 is all the way down there, and we can see is not on the graph. So not only is this function not even, it's also not odd. So this function is neither even nor odd. Now we're going to determine if a function is even, odd, or neither from the equation. The way we're going to determine if a function is even, odd, or neither is through the definition. The first thing we're going to check is to see if it's even. And we're going to do that by finding f of negative x. F of negative x means I'm replacing x with negative x in our equation. And make sure you are careful with parentheses. Keep your negative x in parentheses. Then from there, we're going to try to simplify. Well, negative x to the 6 means we're multiplying negative x to itself 6 times. Well, if I multiply an even number of negatives together, I know the answer is going to be positive. So I get x to the 6 without the negative. Same thing goes for x squared, and 4 stays 4. Notice how our f of negative x, after we simplify, is exactly the same as f of x. So we just showed is that f of x equals f of negative x, which is precisely the definition of an even function. So our function f of x is even. Now, once when we determine a function is even, we don't have to check to see if the function is odd. The reason being there's only one function that is both even and odd, and that's the function f of x equals 0. Now we're going to test to see if g of x equals x cubed minus 4x plus 2 is even, odd, or neither. But just like in the previous problem, we're going to test to see if g of x is even by first evaluating g of negative x. One thing to note, even though in the definition of even or odd, we use f of x, it doesn't matter what we name the function. We can replace the f with a g, an h, or a k, and the definition is still the same. So we'll still do the same test. So in g, we're going to replace x with negative x, and we have negative x quantity cubed minus 4 times negative x plus 2. Well, if I multiply negative x to itself 3 times, my answer is going to be negative, and x times x times x is x cubed. So I get negative x cubed without the parentheses. For the negative 4 times negative x, I get plus 4x, and then plus 2, nothing to simplify. Notice how g of negative x is not the same as our g of x. More specifically, if we look at these two terms, comparing them, the x cubed minus 4x versus the negative x cubed plus 4x, we can see these two functions are not the same, and there's nothing I can do to simplify to make them the same. So from this, we can tell they're not even. From there, I need to test to see if my function is odd. The way we're going to test for odd is now we're going to find negative f of x, meaning I'm going to multiply my original function by -1. When I distribute in the -1, we get negative x cubed plus 4x minus 2. To test for odd, we want negative g of x to be equal to g of negative x from the definition. But if we compare the two, 2 out of the 3 terms are the same. The terms that are not the same is g of negative x has a plus 2, negative g of x has a minus 2, and there's no way I can simplify from there. So g of negative x is not the same as negative g of x, so our function is not odd. So our conclusion, g of x is neither even nor odd. It's not even because g of x did not equal g of negative x, and it's not odd because g of negative x does not equal negative g of x. But now we've completed how we're going to test for even and oddness. First, we're going to find f of negative x, which is going to tell us if our function is even or not. If it's even, we're done. We can move on to the next problem. If it's not even, we can move on to step 2, finding negative f of x to test to see if it's odd. If negative f of x is the same as f of negative x, then our function is odd. If not, then our function is neither. Now we're going to determine if h of x, which equals x to the 5th plus x cubed, is even, odd, or neither. We'll start by testing to see if h of x is even by finding h of negative x. This means we're going to replace x with negative x inside of our function. And since we're raising negative x to odd powers, we're going to get negative answers. So negative x to the 5th would be negative x to the 5th without parentheses, and then minus x cubed. Now, h of negative x is not the same as h of x. We can see the signs are different. So h of x is not an even function. Now we're going to test to see if it's odd by finding negative h of x, which means I'm going to multiply my function h of x by -1. Then distribute in the -1, and we get negative x to the 5th minus x cubed. Now, in order for our function to be odd, h of negative x has to be equal to negative h of x. Well, if we check our h of negative x and our negative h of x, we can see that they are both the same. They're both negative x to the 5th minus x cubed. So h of negative x equals negative h of x, which means h of x is an odd function. Now we're going to determine if k of x, which equals x squared plus 2 over x cubed minus x, is even, odd, or neither. So the first thing we need to do is test to see if it's even, which we'll do by finding k of negative x. So we get negative x quantity squared plus 2 all over negative x quantity cubed minus negative x. If we proceed to simplify, negative x squared would just be x squared, and in the denominator, negative x quantity cubed would be negative x cubed, and then negative x would be plus x. Now, we can already tell this function is not going to be even. If we compare the numerators, we can see that they're the same, but our denominators are not the same. The signs are opposite in the denominator, so our function is not even. So let's move on to odd, which means we're going to multiply our function k by -1. Now, keep in mind, since we're multiplying by -1, multiplying by -1 with fractions is the same as multiplying by -1 over 1, or we can treat the -1 as 1 over -1. Both of these versions of -1 will still give us the same answer, just looking differently. If I do the top one, I'm just distributing -1 into the numerator, whereas with the second version, I'm multiplying -1 into the denominator. Now, the reason why I'm considering both of these options is because we do need to compare with k of negative x. Keep in mind, both of these expressions are equal. But if I just looked at the negative x squared minus 2 over x cubed minus x, comparing it with our k of negative x, we might be tempted to say that k of x would not be odd. But if we look at the alternate way of writing the negative k of x, where we multiply the denominator by -1, we can see that they are the same. So indeed, negative k of x does equal k of negative x, and our function k of x is odd. Be careful testing to see if a function with a rational expression is even or odd. Multiplying by -1 is either the same as multiplying the top by -1 or multiplying the bottom by -1. You may want to look at both options before you conclude for sure whether or not your function is even or odd. Now we're going to discuss how to apply transformations to obtain graphs from basic functions. First, you need to start off by identifying what basic function we're transforming. Recall from the beginning of the section the list of basic functions and their graphs. There is no set order in which you have to perform the transformations. Typically, I like to do my horizontal transformations before my vertical. Now, within each category, horizontal or vertical, they do have their own order that you should perform them in. When you're performing multiple horizontal transformations, you want to follow the reverse of the order of operations. Addition and subtraction indicates horizontal shifts. Since the last operation in order of operations is addition and subtraction, you want to first do your horizontal shifts. Since the horizontal stretches, shrinks, and reflections are indicated by multiplication, you're going to do those last. Now for the vertical transformations, when you want to perform multiple vertical transformations, you're going to follow the order of operations, which means you're going to do the transformations indicated by multiplication, which would be the vertical stretch, shrinks, or reflections, before you do any vertical shifts. You can do the vertical transformations before the horizontal or the horizontal before the vertical, but I do prefer to do the horizontal transformations first, since I have to remember that we're reversing order of operations and that the indicators are opposite of what we would usually expect. Now we're going to graph f of x equals the absolute value of x minus 1 minus 2. Because of the absolute value bars that we see in the function, we can tell that this function f of x is a transformation of the absolute value function. So to start graphing, we're going to start with the graph of y equals the absolute value of x. Recall from the table at the beginning, the absolute value function looks like a v, and the points we're going to use to graph are going to be where x equals 1, 0, and -1. The reason why I'm picking 1, 0, and -1 for the x components is because they're very easy to plug into the absolute value. The absolute value of 1 is 1, so we'll have the point 1, 1. The absolute value of 0 is 0, so we'll have the point 0, 0. The absolute value of -1 is 1, so another point will be the point -1, 1. Now we'll plot our points and connect them with the appropriate shape. And there's my graph of y equals the absolute value of x. Now I can either perform my horizontal transformations or my vertical transformations. My personal preference is to do the horizontal transformations first. To determine what horizontal transformations I need to perform, I'm going to look within the absolute value bars. Looking inside my absolute value bars, I can see I'm subtracting 1 from x, and that -1 is telling me I'm going to shift my graph to the right 1 unit. This is the same as adding 1 to each of my x components. So 1, 1 moves to 1, 0, 0 moves to 1, 0, and -1, 1 moves to 0, 1. Now I'm going to plot the points and connect it up, and there's my graph after I shift right 1 unit. Remember, since we started with a graph that was generally V-shaped, our graph after the transformation should remain V-shaped. Looking back into the function, I can see that the only transformation was the horizontal shift. So now I'm going to go outside of my function and start doing the vertical transformations. Outside of the function, I can see the -2. The -2 tells me I'm shifting down 2 units. This is the same as subtracting 2 from all of my y components. So 2, 1 goes to 2, -1, 1, 0 goes to 1, -2, and 0, 1 goes to 0, -1. Now we'll plot our points and connect them. And in green, we get our graph after we shift our blue graph down 2 units. Since there are no other transformations to perform, our green graph will be the graph of our function f of x. Now we're going to graph f of x equals 2 times the quantity -1/2 x plus 1 squared plus 3. If we take a look at our function, we can see that this is a transformation of the x squared graph. So we're going to start with the graph of y equals x squared. Just like with the previous example, I'm going to use the x components of -1, 0, and 1. And that's because these 3 numbers are very easy to square. And when I square the 3 numbers, I get the points -1, 1, 0, 0, and 1, 1. These 3 points are exactly the same as the points we use for the absolute value function, but the difference here is the shape of our graph. Because we're starting off the graph of y equals x squared, our graph is going to be a parabola rather than the V shape that we saw for absolute value. Now we'll perform our horizontal transformations, meaning I'm going to look inside of the expression being squared. Looking at the expression being squared, I see 2 things happening to x. It's being multiplied by -1/2 and adding 1. When we're doing the horizontal transformations, we want to think about reversing the order of operation. The last operation I would perform is addition by 1, which means the first transformation that I should perform is the one indicated by the addition of 1. The +1 tells us we're going to shift left 1 unit, which means we're going to subtract 1 from each of our x components, and we get the points -2, 1, -1, 0, and 0, 1. Just like before, we're going to plot our points, but when we connect them, we're going to connect them with a parabola since we're still transforming the x squared graph. And there's our graph in blue of what we would get after shifting left 1 unit. Now looking back inside our function, we can handle the -1/2. The -1/2 tells us we actually have to do 2 transformations. First, we have a reflection over the y-axis, and we have a horizontal stretch. We can do both of these at the same time, just by dividing each x component by -1/2, and dividing by -1/2 is the same as multiplying by -2. So after dividing each x component by -1/2 or multiplying each x component by -2, we get the points 4, 1, 2, 0, and 0, 1. Now we'll plot the points and connect the dots, and there's our graph after we reflect over the y-axis and perform a horizontal stretch. But now that we've finished all of our horizontal transformations, we'll turn our attention outside of the function and start performing our vertical transformations. Outside of the function, I see 2 things occurring, multiplication by 2 and adding 3. Since we're doing the vertical transformations, we're going to follow order of operations, meaning I'm going to do the transformation that is indicated by multiplying by 2. The multiplication by 2 outside the function tells me I have a vertical stretch. To do the vertical stretch, I'm going to multiply each y component by 2. And when I do, I get the points 4, 2, 2, 0, and 0, 2. Now we'll plot our points. One thing to note, since I didn't have a reflection over the x-axis, my parabola is still going to open upwards. So now connect the dots, and there's my graph after the vertical stretch. Now, for our last transformation, we have the +3 outside the function, which is telling us we'll shift up 3 units, which means I'm going to add 3 to all my y values, and my points are going to be located at 4, 5, 2, 3, and 0, 5. And there's my graph of the result of my vertical shift in orange. Now I've completed all of my transformations, so the graph in orange is our graph of f of x. And to better help us see our end result and compare it to the graph we started with, I erased the graphs that we obtained from steps 2, 3, and 4.